Most people believe Earth is naturally a warm planet. It's an assumption so familiar that almost nobody questions it. But the geological record tells a very different story. What we call a normal Earth may not be normal at all. If that's true, then we've been thinking about Earth's climate the wrong way. The real mystery isn't why ice ages happen. It's why we ever came to believe that a warm Earth was the default. Part of the answer is simple. This is the only kind of Earth civilization has ever known. Agriculture. Permanent settlements. Cities. Writing. Trade. Science and modern industry all developed during the same warm interval. Temperatures changed, droughts came and went, coastlines shifted, individual societies rose and collapsed under changing environmental pressures. But compared with the enormous transformations preserved in the geological record, the climate experienced by human civilization has remained within a remarkably narrow range. Our experience became our definition of normal. The problem is that human experience covers almost none of Earth's climate history. To see beyond it, scientists must rely on evidence preserved by the planet itself. Sediments accumulating on the ocean floor contain the remains of microscopic organisms whose chemistry changed with the temperature of the water around them. Layers of ice preserve bubbles of ancient atmosphere. Pollen trapped in lake beds reveals which plants once grew in places now occupied by completely different ecosystems. Rocks record the movement of glaciers, the chemistry of vanished oceans, and the presence of ice in regions that are warm today. Together, these records reveal something important. Earth does not repeatedly return to one permanent climate. It has occupied radically different climate states. During some long periods, the planet was much warmer than it is now. Large permanent ice sheets were absent, sea levels were higher, and forests extended into regions close to the poles. Scientists often describe these conditions as greenhouse climates. At other times, ice expanded across enormous parts of the planet. During the most extreme episodes, glaciers may have reached tropical latitudes. These episodes are often associated with what scientists call snowball Earth. Earth has no single climate default across its entire history. A warm planet is not always abnormal, and a cold planet is not always normal. The answer depends on which chapter of Earth's history we are examining. Today, Earth occupies an icehouse state. An icehouse does not mean the entire planet is frozen. It means permanent ice exists at one or both poles, and the climate system is capable of supporting large continental ice sheets. The current icehouse began tens of millions of years ago. But even that enormous span of time has not been climactically uniform. Temperatures continued to change. Ice sheets grew and retreated. Ocean circulation shifted. Greenhouse gas concentrations rose and fell. Then, about 2.6 million years ago, Earth entered the Quaternary period. This is the scale that matters most for our question. During the Quaternary, Earth has repeatedly moved between long glacial periods and shorter warm interglacials. These are not separate ice ages appearing and disappearing at random. They are different phases within the same broader glacial regime. For much of each cycle, enormous ice sheets covered large parts of the northern hemisphere. At their greatest extent, ice covered most of Canada and reached deep into what is now the northern United States. Northern Europe disappeared beneath thick ice. Mountain glaciers expanded far beyond their modern limits. So much water became trapped on land that global sea level fell by more than 100 meters. That did not simply make the world colder. It physically reorganized the planet. Areas now separated by ocean became connected by dry land. Britain joined continental Europe, and Siberia connected with Alaska across Beringia. Crossing between Asia and North America would not have required a boat. Large parts of Southeast Asia became a continuous landmass, while coastlines extended far beyond their present locations. The map humans recognize today temporarily disappeared, and geography was only part of the transformation. Vegetation zones shifted toward the equator. Regions now covered by forests became grassland, steppe, or tundra. Rainfall patterns changed. Deserts expanded in some places and contracted in others. Ocean currents redistributed heat differently around the globe. Animals and early humans migrated through landscapes that no longer exist. Then the system changed direction. Ice sheets retreated. Sea levels rose. Forests spread northward. Rainfall patterns shifted again. The planet entered a warmer phase known as an interglacial. We are living in one of those phases now. The current interglacial is called the Holocene. It began about 11,700 years ago, after the end of the last major glacial period. From the perspective of human history, 11,700 years feels ancient. It contains nearly everything we think of as civilization. From the perspective of the Quaternary, however, it is a brief interval. The same climate can feel permanent on a human timescale and temporary on a geological one. The Holocene feels normal because it contains almost everything humans recognize as history, but across the Quaternary, Earth has generally spent more time under glacial conditions than inside warm interglacials like the one we inhabit now. The cycles varied in length, intensity, and rhythm, but the broad pattern remained. Longer glacial conditions were repeatedly interrupted by shorter, warm intervals. So why do those warm intervals appear at all? The first part of the answer lies in Earth's orbit. Earth does not move around the Sun in exactly the same way forever. The shape of its orbit slowly changes. The tilt of its axis changes, and the direction in which that axis points slowly rotates, like a spinning top beginning to wobble. Together, these changes are known as Milankovitch cycles. But their importance is often misunderstood. They do not simply make the entire planet receive dramatically more or less sunlight. The change in total energy is relatively small. What matters is where sunlight falls, and during which season. Large northern hemisphere ice sheets are especially sensitive to summer conditions at high latitudes. A severe winter does not automatically create a larger ice sheet. Snow can accumulate for months and still disappear if the following summer is warm enough to melt it. For an ice sheet to grow, some snow must survive the summer. If high northern latitudes receive slightly less summer sunlight, more winter snow remains on the ground. The next winter adds another layer. Over time, that snow is compressed into ice. Then the climate system begins to amplify the change. Bright snow and ice reflect much more sunlight than dark soil, rock, or ocean. More ice means more sunlight reflected back into space. Less energy is absorbed by the surface. Temperatures fall further, allowing even more ice to survive. This is the ice-albedo feedback. The reverse happens when summer melting exposes darker ground and ocean. Those surfaces absorb more energy. Warming increases. Ice retreats faster. But ice is only one part of the response. Oceans store and redistribute enormous amounts of heat. Changes in ocean circulation can alter climate across entire regions. Carbon dioxide also rises and falls during glacial transitions, strengthening either warming or cooling. The orbital changes help pace the rhythm. The climate system determines how strongly Earth responds. Milankovitch cycles are not a single switch that turns an ice age on or off. They provide the changing push, while ice sheets, oceans, greenhouse gases, and other feedbacks determine the scale of the response. The result is not a perfect clock. Different orbital configurations can produce different outcomes because the climate system is never starting from exactly the same state. But warm interglacials are expected phases within the Quaternary glacial system, and they do not last forever. Modern warming may seem to challenge everything we have just learned. If Earth naturally moves between glacial and interglacial conditions, it may seem reasonable to assume that modern warming is simply another part of that ancient rhythm. But the evidence does not support that conclusion. The Quaternary rhythm unfolds over tens of thousands of years. Modern warming has accelerated over roughly the last century and a half. The mechanism is also different. Orbital variation slowly redistributes sunlight across seasons and latitudes. They do not explain the rapid rise in global temperature observed since the Industrial Revolution. Modern warming is driven primarily by the increase in greenhouse gases produced by human activity, especially carbon dioxide released through fossil fuel combustion. Industry and land use change. That does not erase the Quaternary cycle. It adds a powerful new forcing on top of it. Earth still has orbital cycles. Ice, oceans, vegetation, and carbon still interact. But human activity is now changing the atmosphere much faster than the orbital processes that pace glacial cycles. These are not rival explanations. One describes the long-term rhythm of the Quaternary. The other explains the rapid warming occurring inside the current interglacial. Separating them prevents two opposite mistakes. Natural glacial cycles do not prove that modern warming is natural. And modern warming does not mean the Quaternary glacial regime never existed. Both can be true, because they operate through different mechanisms and across different timescales. But the Holocene matters for more than its temperature. It also provided long stretches of relative climatic stability. That stability did not eliminate droughts, floods, cold periods, heat waves, or regional collapses. But compared with the enormous transitions between glacial and interglacial worlds, its environmental boundaries remained familiar long enough for societies to build around them. Civilization did not merely appear during a warm interval. It built itself around one particular climate configuration. Climate became part of civilization's architecture. Ports were placed where the coastline existed. Farms developed where seasonal rainfall supported crops. Reservoirs were designed around expected river flows. Roads, power systems, and cities assumed that these environmental patterns would remain within a familiar range. That is why our idea of normal feels so convincing. It is reinforced every time we look at a map. The continents appear fixed. The coasts appear permanent. Forests seem to belong where they currently grow. Deserts seem naturally assigned to their present locations. But during the Quaternary, all of those boundaries moved. Sea level rose and fell. Ice sheets advanced and disappeared. Habitats migrated. Land bridges opened and vanished. The world humans inherited is not the permanent shape of the planet. It is one temporary arrangement created by a climate system that has repeatedly produced very different worlds. So the geological record does not tell us that Earth is always supposed to be cold. It tells us something more precise. Across its full history, Earth has occupied many different climate states. Within the Icehouse state Earth occupies today, the Quaternary has been shaped by repeated glacial cycles. And within that rhythm, the warm climate of the Holocene is an interglacial interval, not the condition that occupied most of the cycle. That is the distinction human experience hides. We did not watch the ice sheets advance across continents. We inherited the landscape after they retreated. We did not watch sea level rise from its glacial low. We built ports along the shoreline it eventually reached. We did not experience the full quaternary rhythm. We arrived during one warm movement inside it and treated that movement as the background of reality. The real mystery was never simply why ice ages happen. It was why a species living inside one interglacial came to imagine that the interglacial was the planet's default. We thought Earth was naturally warm because we mistook one interglacial for the entire story.